In 26.48, you can see the picture on the top left. There's a circuit. It's an RC circuit with a battery. It's got a switch. When they move the switch to position 2 over here, okay, it's going to make it so that the battery is in contact and it can start to charge. Okay, so they're going to first they ask what the charge on the capacitor is going to be a long time after the switch is moved to position 2. You know that a long time is a magic word saying basically lots and lots of time constants. So basically forever. At that point, the charge will be just all of the same voltage as the battery. So it'll be E times the capacitance. So it'll be 28 volts times the 5.9 microfarads times 10 to the negative 6 farads. When you multiply that together, you get 1.65 times 10 to the negative 4 farads. Or, because it's going to be convenient later, I'm going to convert it to 165 microfarads. For B, they say after you put that switch for 3 milliseconds, the charge on the capacitor is going to be 110 microcoulombs. You can see the problem right there. Okay, what's the value of resistance R? Notice they haven't asked that at all yet. What's the value of resistance R? So we're going to look at the expression and we're going to move it around to find out what R is. Okay, for a charging capacitor, the charge is going to be equal to the final charge, whatever the charge is going to be at the end, times 1 minus E to the negative T over RC. We're going to approach that as we go. Okay. And we're fortunate because we know both of these things. We're going to move those around. So we're going to say Q over Q final equals 1 minus E minus T over RC. Okay. I'm going to subtract 1 from both sides, and I'm going to multiply by negative 1. So I'm going to have E to the negative T over RC equals 1 minus Q over the final charge. Okay. Then I'm going to take the ln of both sides. So the natural log of that big expression, 1 minus Q over QF, is going to equal negative T over RC. I'm going to swap the big expression on the left with RC. So then I'm going to have RC equals negative T over the ln of all that stuff. And then I'm just going to get the resistance itself is equal to negative T divided by C times the ln of 1 minus Q over the final charge. It's a little jumpy, but I just rewrote it again. Now we're going to plug all of our information into it. Okay. So minus, we got 3 milliseconds, so it's 3 times 10 to the negative 3rd seconds. We divide it by the capacitance, which is going to be 5.9 times 10 to the negative 6 farads. And the natural log of 1 minus 110 microcoulombs. Remember, they tell us that. Remember, we turn this into 165 microcoulombs. And then when I did all that stuff, multiplied it all together, I got 463 ohms for my answer. Actually, I get volts per amp when I work out all the units, and that ends up being ohms. That's part B. Now, for part C, they ask us how long after the switch is moved to position 2 will it have 99% of the final value found in part A. Well, I thought of it this way. I said, well, for part C. I said that means that that Q over Q final is going to be 0.99. And that means that 1 minus Q over Q final is going to be 1 minus that, which is going to be 1%, which is going to be 0.01. And I went back to that expression that I had over here, that expression of RC equals negative T over ln of 1 minus Q over Q final. Remember we had that one earlier? Okay. And I just rearranged it now to find out what time is. So I'm going to multiply both sides by the expression on the bottom in the denominator and multiply by -1. So time is just going to be, I'm going to put a little line here to separate those. It's going to be negative RC natural log of 1 minus Q over the final charge. Okay. And if I do that, I can just plug in all the information I have. I found the 463. I'm going to use that. And I know that capacitance from earlier, 5.9 times 10 to the -6 farads. And I need to take the natural log of 0.01. Remember, that's all times a negative number, because remember, my natural log is going to give me a negative number. When I multiply all those together, I get 0.0126 seconds. And I'll let you work through the actual dimensional analysis to find out that you end up with a number that is exactly seconds.